All right, welcome everybody. I have a special guest today. Greg, how do you pronounce your name? Is it Slepak?
Greg Slepak, yeah.
Slepak. So I've been talking about your work to some of my students, but for a couple of years now, I've been obsessed with, ever since DigiNotar hack back in 2011, I think it was, 2010, they hacked the root CAs. And I just looked at this root CA list and how things work. And it's just about as secure as Swiss cheese, the way we certify things. So, everybody, is just familiar with blockchain, Bitcoin, most of my students, hopefully. And I've been saying we should probably blockchain that list. But I found out whenever I think I have a great idea, I get justified by when I find out somebody else already had that idea. Greg and many other people have been addressing this for a long time. I found you, Greg, from a 2017 talk. So you beat me by years, and you were far more advanced in thinking this thing through. So thank you so much for coming.
Thank you, Larry.
Oh, it's wonderful. So just to also for my students and Greg, we approach our problems, I think, from opposite side. Greg, your background is you're a developer, right?
That's right.
Yeah. So Greg started here and worked his way down, and Larry is just a grunt who started connecting wires. In the 80s, I helped wire things out, and to troubleshoot your wires, we learned to look at, you got to know how the network card works. And then we started getting these packet sniffers, and I was able to see packet layer stuff and then say, the application is able to talk, but it's not the network, it's this. And I start working my way up, and we get to the point of, how do I know when I type in www.internetworkdefense, that's where I'm ended up. So we've come up with ways to certify this. And well, my knowledge is
hey, sorry for the delay.
Hey, Tom up the groove. Greg, this is Tom up the groove. Tom, one of my mentor for 40 years. First guy I know to have a computer.
Nice. Hi, Tom.
And you are kind of loud there, Tom. Your mic seems to be dominating. So Tom and I together actually have looked at ways, and been obsessing about this. Well, we're here to have Greg.
Speakers are on mute.
I'm going to mute you, and you can unmute yourself, Tom. But I think you're accidentally talking. So the point of this, and when I type in www, since my students are CISSPs, for instance, when I go to the ISC Square's website, how do I know it's really them? How do I get to this? Well, I sniffed out a quick thing, and my students should know that the first thing you do is a DNS request. And I said, hey, where is www.isc square or whatever, HTTP? And I get an answer. But the answers, the response is not signed. I don't know. I mean, anybody could have said this. Oh, but Larry, they would have to know the transaction ID. It's 16 bits. That's not that long. So we need more than just DNS to tell us, and an unsolicited reply we've seen over and over. So when I went to the ISC Square, I got their certificate. Remember, www.isc square is the X.500 name. To certify that, I have an X.500 certificate. And I can look at the certificate and see who signed it, and then it's like a driver's license. But the problem is, if this is like, where did you get your certificate from? Oh, here's the signed certificate, and the subject is who the certificate's for. Oops.
Yeah, I think if I had approached this problem from this frame of reference, I would have never been able to make any headway.
You know what? You are far over my head, and I might be a little bit under your head, and hopefully we can meet in the middle, sir.
Yeah.
Because I'm.
Now what?
Oh, I think you got unplugged.
Yeah, there's the maker of my headphone has decided to put a button right where it can fall on the floor. Sorry. So Luckily, Microsoft has pre-shipped a list of everybody I'm supposed to trust. Oops. I meant to have this open for you, sorry guys. Oh, there it is. I'm sorry. So all the people I'm supposed to trust. We'll get there, Larry and his live demos. Can be validated. For some reason, that window does not open straight up. By looking at the root CAs, oops, trusted roots. And these are like the DMVs around the world. These are the Federation IDs. I can trust these. So as long as DigiCert, their little DMV, has a certificate too, and they did. They said, oh, they gave me that too. I got the intermediate CA, but DigiCert High Assurance is who validated that. And I don't have to get that because Microsoft was kind enough to put that already here. How do I know this list is good? Because all you have to do is right click it, all tasks, import, and you could import that with a cat video. I have a feeling the ISO didn't put that in there. And now every certificate says check here. So I could say it be anybody. This entire system breaks if any one of these are wrong. And if this were Bitcoin, you would need to break 51% of them. So it's far better. But that's the start. Greg looking at it another way coming down has it got a lot more sophisticated look through this and how the top level domains and DNS can be combined. And I never thought of it, Greg. And I'm so new at it, I don't want to steal your thunder. I'm going to stop sharing and let you take over because I think it's brilliant.
All right, awesome. So I'll go ahead and start sharing my screen or the presentation that I had. So this is these are slides from a presentation that I gave multiple times now. And there is a YouTube video of basically this presentation that we're kind of going to do a quick run through, less prepared version of. If you want to see the really nicely produced version of this, you can go to the OK Turtles Foundation YouTube, and we have a nice, very short video on this. I think it's very, very short. It's like 10 minutes or less. So the title is From DNS to DPKI, or why secure decentralized namespaces are the future. And so who am I? My name is Greg Slepak. That's my Twitter. I started out in my career as a developer working on file encryption software. So in the information security world, InfoSec. And I made an app called Espionage. And then I started a nonprofit called the OK Turtles Foundation, which has done a few different projects. I don't know why the E is missing in group income, but this presentation is about the first one, DNS Chain / DPKI, and specifically DPKI. DNS Chain is an outdated project. We're not really doing any stuff with it right now. We're just pushing the idea of DPKI, or decentralized public key infrastructure. So what is the problem that we're dealing with? The problem is that, as Larry was pointing out, how do you know that when you visit a website, you're actually visiting the correct website and you're not being man in the middle by an attacker? In other words, the internet is engineered to take you from point A to point B, point A being your computer and point B being a server out there. And it needs to figure out how to route your packets to the server and then route the packets from the server back to your computer. And that's kind of the world where Larry likes to live, is looking at all of those packets in Wireshark. I just live in a more theoretical, world. I don't look at packets. I just think theoretically about all of this stuff, a lot more abstractly and high level. If you've got a path from point A to point B, how do you make sure that the communication channel along that path is secure and that you can't have somebody come in between the two of you and start messing with the messages and the communication? So this journey starts when the user enters what is known as a domain into a URL bar. That is where it starts. And actually, what we're talking about, like before the call started, Larry and I was asking me something about whether the work that I'm doing has to do with email or something like that. And in a sense, it does. It doesn't just have to do with email. It has to do with the security of the entire internet and the fundamental ways of securing communication, regardless of whether you're on planet Earth or on a different planet. It doesn't really matter. We're talking about fundamental ways of securing communication between 2 points, wherever they might be. So if the journey starts with a name, and we want to get from a name, and why is this important? There's something called Zuko's triangle, and one of the edges of that triangle is human readable. So the name is the human readable part of what we're dealing with. Okay, so, sorry, the Zoom was notifying me of things. So the name is our starting point, and notice we don't start with an IP address. The IP address is what we want to get to. We don't start with an IP address because it's not easy to memorize. It's not human readable. Humans work well with easily memorizable things, and for humans, those things are names. So that's why we start with a name. Next, step 2. A system called DNS is going to give us that IP address once we hit enter. Larry's talked a lot about in that class, so I won't bore you with the details. But what we know about DNS is that it's not secure. There's no security involved whatsoever in DNS. There's nothing along the line, and what I mean is there's nothing involving cryptography in DNS. And cryptography, by the way, is necessary, but it's not sufficient for the system to be secure. Just because the system uses cryptography doesn't necessarily mean it's secure, as we'll see with HTTPS. So the IP address is then going to send us a certificate. We're going to, by talking to this IP address, or what we think is the IP address, the IP address is going to send us a certificate. And that certificate is going to be validated using a system called SSL or TLS. And the subpart of it, known as X509, is going to be sort of the mechanism by which that certificate is going to be validated. That list of certificate authorities that Larry was talking about, one of those certificate authorities, and the critical point here is that it's any one of those certificate authorities is going to sign off using their private key and say whether or not that certificate is valid. And if they say the certificate is valid, then the lock icon appears. Now, Larry showed you on Windows. This is what it looks like on Mac OS. Each operating system ships with hundreds of certificate authorities known as root certificate authorities. There it is, system roots. And your computer trusts all of them. In other words, if any one of those entities is compromised, then all of your communications are compromised. Because every one of those entities has the ability to make that little lock icon appear and make your computer believe that the connection is secure. So moving on. Oh, and I should also say, not only do they have that ability, they have the ability to delegate their power to another entity. So if they want to say, you know, hey, there's some other organization that wants to get in on this business, we can give them the ability to make the lock icon appear. So it's not just, this is just the root certificate authorities. There are other certificate authorities known as intermediate certificate authorities that have the exact same power that don't appear in this list. So the lock icon appears if one of them has said it's secure. So the problem, DNS only, has no security. There's the man in the middle attack that I was talking about. In DNS, this is perfectly possible. You can ask for an IP address, and the DNS, a malicious DNS server can give you the wrong IP address. Problem 2, HTTPS, the system that was invented in order to fix that first problem, has weak security, as we discussed, because the certificate could be bad, and there's over 1,200 root and intermediate certificate authorities with this power. The way that it looks is your browser asks if the certificate is legitimate, and then someone out of a crowd shouts, "Sure." And your computer's like, "Okay, thumbs up, everything's good." Bam. The connection is secure. Problem 3. And this is kind of what this talk is about, and what we'll be discussing today, is that DNS and HTTPS, they share different namespaces. And for whatever reason, this hasn't really been acknowledged in the attempts to fix this problem. This is a big problem. This is one of the reasons why we're having problems, is because the namespaces are different. So what is a namespace? It is a space with names in it. It's one of the best named things that I know of. It's very self-descriptive. There's no confusion here. So we have a space and there's some names in it. And these namespaces are also known as key value mappings. In other words, in the space, there are names, and when you request a name, you get the value that that name is mapped to. In this case, it could be an IP address. So you ask for su.com, and the value that's returned is the IP address. So, okay, in this slide, I don't even remember what the point was on this slide, but we'll get to a better version of that next. DNS and HTTPS, they share different namespaces. So yeah, this is what I'm talking about with the better version. These are totally different worlds. Think about it. You're using one system called DNS, which has its own kind of inconsistent namespace. It's not actually one namespace. DNS doesn't really give you it pretends to give you a namespace, but as we can see, because the man in the middle attack is so trivial in that world, it's not really a secure namespace, which means that one day or 1 second or 1 millisecond, you could, get one value, one key value mapping, and the next, for the very same key, you could get a different key value mapping because there's a man in the middle attack taking place. So it's not a consistent namespace. And then worse, the system that was invented to address the issues with DNS, HTTPS, that's a completely different namespace. None of the certificate authorities, none of that stuff is connected to DNS in any shape, way, or form. The names that appear in these certificates, they don't originate from DNS. They're just invented out of thin air.
Can I want to interject there because it's so important for my students. And I have to tell you, Greg, I knew this, but I didn't register how ludicrous the system was until I watched your videos. And I was like, that is funny. Why aren't they more homogenized? DNS is this big domain namespace of just IP to name. And HTTPS, which uses an X.509. The PKI is supposed to do this, but there's no IP address in X.509. So already they're starting from different perspectives and they don't talk to each other. And I'm still letting that sink in. Since the last time we talked, I watched your video, but it is amazing and they really should be. So anyway, I'm sorry.
Yeah. So what we end up is a world where we're trying to use a system, like we're trying to solve a very basic problem. It's like, if you think about it, what we want is really simple. We want for a name to give us a value that's an IP address. But the systems that we've invented up to this point are completely broken. They don't do this in any sensible way. They're not even the same system. They're completely.
But I don't know that IP is actually a good thing because IPs mutate all the time. I mean, hopefully Google's number of IP addresses don't change much, but I would rather not be reliant. And I think that's where the HTTPS could help us but still at some point we have to resolve it. So I don't want to steal you because your solution does fit my potential vulnerabilities. But
Well,
I don't know that I need
however that it is done, we need a secure namespace. We need a namespace that where the person who is in charge of that name, of that key value mapping, that's the person that gets to decide what that key value mapping is. And that's not the case today. We give the impression that that's the case, but it's really somewhat misleading because of how insecure it is. There's nothing really guaranteeing it. There's nothing mathematical that's guaranteeing that. And we want something much closer to math to be guaranteeing that key value mapping because it's so important. Because if you don't have something close to math that guarantees it, then you have all kinds of major security problems and data breaches and chaos. So
it addresses to me the number one problem in any solution, whether it's security or developing food. You're developing something for someone, and if you don't know who that person is and you give it to the wrong person, it doesn't matter. If you get the wrong who, it doesn't really. You're protecting good guys from bad guys. Can you tell the difference? No. Well, then I don't care how strong your lock is.
Yeah. So, okay. So the problem is that each of these, as I was saying, this is going over the same point, that DNS and HTTPS each have different namespaces themselves. DNS, as I mentioned, can give you different values for that mapping. One of those values can be true, can be correct. The other one can be incorrect. How do you know? You don't. And HTTPS, the exact same problem. There's a bunch of different namespaces in HTTPS because each one of those certificate authorities can invent its own namespace on the fly. So there's no consensus about what these key value mappings should be. And that's the real problem, is that there is no consensus. So we need to introduce consensus to solve the problem. So yeah, these are the 4 problems. So one solution is to combine these 2 systems into a single namespace using decentralized consensus. That's the solution. We have to introduce consensus, and it has to be decentralized, because if it's not decentralized and we have a centralized consensus namespace, you have an insane political problem where a single entity has control over these key value mappings and nobody else does. So if you want to give control to these key value mappings to their owners, you need a decentralized consensus namespace. So what's this about? Bring out your dead. This is from Monty Python. And we're going to be talking about the attempts to fix this problem that have taken place in the past and have failed. So we got X509. We just covered it. DNSSEC. DNSSEC is complicated, expensive to deploy. It's unnecessary also because we want a single system and not 2 separate systems with HTTPS on the one hand and DNSSEC on the other hand. We want to have a single consensus namespace. And DNSSEC doesn't really improve much on X509. It's broken. It doesn't work very well. These are the outages and failures from a couple years ago.
DNSSEC isn't separate from X509. In fact, for DNSSEC to work, the DNS server needs an X509 certificate. And if that's broken, DNS can't be trusted. But it's not separate. It actually requires,
maybe they use X509 techniques and methods. What I mean is that it's not part of HTTPS. So both HTTPS and DNSSEC
all use X509.
They both use the concept of certificates.
Yeah, and my students need to know it. It is an X.509 certificate, whether it's a DNS. We need to know it's the trust anchor signer. That's what your primary DNS is going to have.
Yeah.
You have an X.509 certificate.
That's a technical point. That's fair.
Oh, I'm sorry. I just want to make sure that it doesn't matter, because your theory is if PKI is broken, and it is, DNS.
Yeah. So in other words, they both use this mechanism of certificate authorities and certificates to sign things. But what I'm saying is that DNSSEC, from a trust perspective, is a separate kind of thing, because you've got the root certificate authorities that are trusted by the computer. And then you've got this DNSSEC world where you've got a separate set of certificate authorities.
From the viewpoint of the
yeah,
client, it's a
yeah.
separate, a totally separate handshake, and they don't talk to each other.
Right. Yeah, exactly. Totally separate. Thank you. Okay. So it doesn't need to be a separate handshake. It could be one. So is it less secure than 509? I'm actually not entirely sure. It's maybe maybe it is, maybe it isn't, but it's about the same. It has the similar problems. So convergence perspectives, and we can talk a little bit in more detail about DNSSEC later, because I'm going to go. It depends on how much time we have. Because there's an excellent presentation from HNS that I can show, which has better slides than I do on DNSSEC, and it shows kind of how that world works, which is slightly different from the way that HTTPS uses certificate authorities.
I will gladly let you go as long as you would like. This is the DNSSEC stuff is especially important, students. If you've done your cloud, you know you've seen your practice exam questions on it. But there was also in this document that came out where they want to strengthen email with DNSSEC and HTTP between the, and I tried to roll it out, Greg, and that's part of how I found you. And I was like, he's so right, it's not working. And I was trying as recent as I migrated to AWS. Route 53 supports his DNSSEC, and it's not right. It's not right. So that's why so as long as whatever you can share is going to be useful for me and my students, I'm sure. Thank you.
Is there, okay, quick question, Ishar. Is there any enterprise that actually implement DNSSEC? I work for a large enterprise. I don't think any, do you guys know who actually have DNSSEC working top level? Anybody out in Google maybe?
I only know the root servers. I really don't know any organization that actually told me they rolled it out.
Greg, DNSSEC's been around. I can't remember. It's like at least 20 years old. Has anyone done anything? It's one of the things that we all heard. I'm in security field. I hear all the time, but I have not seen anybody who actually do it end to end.
Yeah, I don't know. And, you know, it's honestly a good thing that almost nobody does it, because if more people did it, we'd be stuck with a bad system.
Oh,
so,
good.
Yeah.
So then they've been preaching to us since like my first step on DNS. You need to DNSSEC it. And I'm like, well, what does that mean? Right.
Yeah.
But it's actually a broken system. So it's a good thing we didn't have a traction. Is that what you're saying?
That's what I'm saying. Yeah.
And that's the problem with my students too, Shar. You just brought my students have to learn what you're being taught, that we have to roll it out. And I think Greg's absolutely right. It's never going to come out. It's never going to come
I'm glad, and I didn't do it. Oh, I have to run, but it's really interesting. This is really good. I have to hear the recording. I have to 1:30 meeting, but keep going on.
Thank you for the question. Yeah, thank you. All right, so convergence perspectives. This was an interesting project. These were two different projects done by different teams. One of the people behind these teams was Moxie, Marilyn Spike, the same guy behind Signal, the Signal Messenger. I think that was convergence that he worked on, and they both do the same thing. What they try to do is they try to actually, you know, it's a good thing. They try to add consensus, which is what, you know, I was saying earlier, we need to do is we need to add consensus. And they tried to add consensus back on top of the system by essentially, like, I don't even remember the exact details, but it was like by querying your route to the, by querying a separate set of servers, if I recall correctly, that try to, like, if you're trying to visit google.com, these other servers are going to also visit google.com, and they will see what the certificate is that's being returned from google.com. And then you will talk to the convergence servers, and you'll be like, is the certificate that I'm seeing the same one as the one that you guys are seeing? And if so, the connection is considered secure. If not, then it's not. Now, this is like a Band-Aid onto the problem, because you now have to, like, it's from an engineering perspective, it's a really ugly solution to the problem, because you've got all of these separate systems. You've got DNS, a DNS connection going out, then you've got this TLS connection going out for HTTPS, and now you have another TLS connection going out to these convergence servers to make sure that it's like layers of Band-Aids, because the fundamental approach is wrong. You got one Band-Aid on top of another Band-Aid on top of another Band-Aid, and it's just an ugly mess. So this is, speaking of ugly messes, what is it? Certificate transparency is another attempt, is another band-aid to attempt to fix this problem, because we don't have an effective solution to this. So okay, I'm not going to go over this. It's just not, we don't have the time for it, and it's not important. It was talking about the how the systems compare to each other. So what we need to do is introduce consensus. It's when a group of independent entities agree on a decision, like if a key value mapping is valid by voting on some threshold, typically greater than, and the voting threshold should be greater than 50%. So one more attempt to fix this problem was DNS Script. DNS Script is kind of like DNSSEC, but it's maybe even a little bit better in some way. What it does is it secures the DNS connection between you and the DNS resolver that you're talking to. So it doesn't, if your DNS resolver has the wrong value in it because its upstream connection to the root DNS servers was wrong, was man in the middle, then DNS Script is not going to protect you. But if your connection to between you and the DNS server, that one, it will protect. And you know, it's not bad, but it's not great. Yeah, because as I said, it doesn't protect against upstream man in the middle, and it's also difficult to use. Pinning, HPKP, they actually got rid of this. Google introduced pinning, and they removed it later on in their browser. The idea of pinning is that this is how Signal works, actually. The Signal messenger uses something called TOFU, or trust on first use. So what that says is that the very first time that you see a certificate, you're going to save that certificate essentially locally, and you're going to pin it so that if it changes the next time, you're not going to trust the change. And pinning, you know, adds a few more rules. It says it can say, for example, that only these certificate authorities are allowed to change the certificate. If it's changed, if you see a certificate from any other certificate authorities, know that it is bad. This is a great solution to the problem, because it actually does solve the problem, but it does have a downside in that it can break things. If, for example, the system administrator who is managing the website decides to change the certificate authority that he's using, the entire website at that point is bricked for everybody who who visited it beforehand.
Or even that CA just goes out of business, you know.
Or if that CA goes out of business or something like that, yeah. And there are other potential issues. Another potential problem with this approach is that if the connection is man in the middle initially, it can be used to through TLS man in the middling. You can add pinning to websites that didn't have them previously, maliciously add pins, right, and break those websites.
And that's, you know, you gave me I've seen the acronym and I never jailed it. You trust on first use TOFU, and I love that concept. And I'm sitting there going, and it's with anything. It's like, you know, your antivirus. All right, this is the clean version. You know, I hope it's clean. So as long as that's true, though. Great.
Yeah, so pinning's not bad. It works in some use cases. For example, on Signal, it works really well. You'll see a message, you know, this person's keys have changed, and that tells the user, you know, if they know what that message means, that they should in person verify those keys. But most people aren't going to do that, first of all. So it's a little bit clunky. There's better solutions than pinning. So what are those better solutions? Yeah, it's also ineffective against man in the middle on first visit.
It just isn't dynamic enough. It's not agile.
Yeah, exactly. And it's also broken for users with broken clocks. It's another interesting factoid about it. So certificate transparency, Connix, and DPKI. Okay, so these are new attempts.
Google's slide. Please stay on this, because I love this slide.
Yeah, so we OK Turtles, and by we, I really mean I spent a while studying these different systems and then trying to see, what do these systems do? How do they stack up against each other? And certificate transparency may be able to detect man-in-the-middle attacks. The idea is that if you get enough certificate authorities to join this system, it's yet another totally separate system that needs to be involved. And by the way, this is another nightmare about these band-aids, is that the more band-aids you start adding on top of one another, the more centralized the internet itself is going to get, because it will become more and more difficult and complicated for anybody to run a website. Because they have to learn about all of these different systems. It's the same exact problem that's happening right now with email. Because to run an email server, you need to make sure that your email server is complying by 3 or 4 different protocols to deal with anti-spam measures. And it's really quite a nightmare. So certificate transparency introduces this whole other system that involves all of these other servers that the certificate authorities need to send a copy of the certificates that they issue into this log that they're keeping. It's kind of blockchainy. There's a log of certificates that needs to be out there. And so somebody needs to be monitoring this log and see if, and this is the other problem, is that if effectively people need to be monitored, the people who are interested in their own websites need to be monitoring all of these other logs out there. And remember, there are so many different certificate authorities out there. So what are they suggesting? That if you're a website owner, you need to be monitoring 1,000 different logs to check and see if any one of those logs misissued your certificate? That's essentially what they're saying people should be doing. Nobody's going to do that. So and by the way, it also does not prevent the man-in-the-middle attack, which can still happen without any problem and go completely undetected potentially. And the only thing, so after your entire company has been breached and all of your data has been stolen and you're out of business, then Google comes in as the savior and says, well, at least you'll be able to look at these logs and see that somebody, maybe you might be able to find the log out there that says who was the responsible party for the fact that your business just got exploded. I'm
picturing the smoke detector that doesn't sound an alarm. And then so after everyone burned out, at least the smoke detector did register a fire.
Yeah. So that's the idea behind certificate transparency. And I just don't understand how anybody could promote this. So Connix is another system that actually does prevent man-in-the-middle attacks. It relies on novel zero-knowledge proof cryptography, and it may be a decent system, but it is one of those band-aidy type systems. And it's also not censorship resistant. So that's kind of a downside with it, is that if you're into censorship resistance, then you might not like Connix as much. And then finally, we get to DPKI. So DPKI checks all of these boxes. It obviously detects man-in-the-middle attacks because it prevents them. It is censorship resistant because it's decentralized. Connix is not. It's centralized. It's resistant to denial of service attacks, again, because it's decentralized. Is it scalable? We think it is. So we think, yeah, probably it is internet scalable. One of the reasons why there's probably not a green check mark there is because it really depends on, there's something called the DCS theorem and the DCS triangle, which says that decentralized consensus systems can have 2 out of 3 properties. Decentralized, they can be decentralized, they can have consensus, and they can scale, planetary scale. And you can have almost 2 of those and not necessarily all 3. There are ways, however, to work around that triangle. And that's honestly
well, I was going to get in that because I watched your video again. They said I wanted to prepare. And I was wondering, is that the reason for each, or one of the many reasons, I could come up with a couple of good reasons for each top level domain to be on a different chain? And that prevents some of, okay, so that would help the scalability by having different chains there.
Yes, it would help the scalability and it would prevent decentralization for some of these TLDs to be on different chains. Yes. So DPKI, let's get into it. The solution is to combine DNS and HTTPS into a single namespace using decentralized consensus. That's what DPKI is all about. For each TLD to be on its own decentralized consensus based namespace. So this is a little bit outdated, this slide, because it implies that it's one TLD per blockchain, and that could be an approach that is done. Yes,
Yeah, I had a feeling you didn't mean that because I'm picturing like 100 different Ethereum versions, and they could be their own different Ethereum.
Right. That would actually be a very secure and decentralized system. But these guys who are doing things lately are not doing it this way. Handshake that we're going to talk about, they're taking multiple TLDs, and their approach, I'm not necessarily saying it's bad. It has its pros and cons. Handshake maybe in a sense muscling their way into getting DPKI off the ground. They have really been dealing with the political side of getting this entire system up and running. So I'm not gonna badmouth them because they're doing what they need to do to get this stuff.
For now, this is to get from A to B, but we're not. We've got a few steps to get to C.
Yeah, because the existing system is very entrenched and it's difficult to change it.
Sure.
And there's a lot of interests out there who don't want DPKI because it would render their business obsolete in a sense.
Well, here's a perfect thing. My students have to deal with data loss prevention systems and other SSL man-in-the-middle attacks. So when I have an internal employee going to LinkedIn and he's not accidentally posting internal secrets, so they actually do have to have a man-in-the-middle type kind of thing, that does it for them. And does this break their ability to do that?
Well, that's I mean, you can always make a system less secure. So yeah, there's always ways. So if you want to do a good man in the middle, for example, to have your business,
I have a DLP domain, and then the application goes, and no, because we're on the DLP network. Whenever you go to Google, and you're going to have to go through the DLP.
Yeah, they're a way of constructing these, your own internal network and your own internal systems, so that you can man in the middle your own traffic if necessary.
Yeah. Sure.
Okay, so why blockchains? Centralized namespaces versus decentralized namespaces. What is this talking about? I haven't done this talk in a while. That's why I'm kind of here with you people, like discovering this anew. Okay, so global. Who controls the name mappings? Not you, right? Centralized namespaces, obviously you don't control the name mapping because some other entity does that's managing this namespace. It's incapable of providing ownership of an identifier and incapable of censorship resistance. Decentralized namespaces, on the other hand, due to their decentralization, actually provide a realm that does give people, the end users, ownership of their names. And it also gives them censorship resistance. So as long as they remain decentralized, because decentralized systems can always be captured with consensus capture. Why multiple blockchains? Right. So we're talking about this. There really does need to be. We can't have Handshake be in charge of DNS and HTTPS for the entire internet. That would be a bad outcome. There needs to be competition to Handshake because, and I hope the Handshake people understand this, because if the Handshake blockchain becomes the one go-to stop for all of these namespaces, they are at risk of consensus capture of a single entity controlling that entire chain. Because of the DCS triangle. Theoretically, that's the reality of it. So Zuko's triangle, okay, so this and the DCS triangle, right? So cannot have just one blockchain. That's what I've been talking about. DPKI is different, has to be different, relies on consensus, recognizes consensus capture. Consensus capture, right, consensus capture is when you have a group and the consensus participants, the people who are doing the voting, initially the group, everybody in the system has a vote. But with the more users that the system gains, the fewer percentage of those users can actually vote on the contents of that chain. So eventually, fewer and fewer participants that are using the system are consensus participants. Until you get a situation where, like with Bitcoin, there was actually a point in time where there was one company that was mining more than 51% of the hash rate for Bitcoin. It didn't last too long, thankfully, but that did happen.
China had 74% until they kicked them out in what was it, July of 21.
That's true.
74% of the miners were in China.
Exactly. But even though they were different companies, they were all under the Chinese government's jurisdiction. So effectively, a single government did have for a very long time control of the Bitcoin blockchain. And I don't know why China decided to kick them out, because I think that was dumb. But they
extremely good. They wanted full control, right? A great,
it was good for Bitcoin that they kicked them out. It improved the security of Bitcoin. Okay, DPKI does not specify specify consensus. It is a protocol, right? So DPKI is not a consensus protocol the way that proof of work is a consensus protocol. It is a protocol or an idea for consensus protocols. It's saying we got these different consensus systems out there. We've got ENS, we've got HNS, Handshake, we've got Namecoin. Let's have all of these systems. Let's bring them all together. Throw them into, throw out the root certificate authorities, throw in these blockchains, essentially. Replace the root certificate authorities or amend the root certificate authorities with these blockchains. And that way you can have some namespaces that are actually secure and reliable. So that's all of this. Okay, yeah, and they have to be independent. That's what we're talking about. Okay, so yeah, this is the end of the talk for that presentation, and it's talking about potentially DPKI-friendly projects. Of these projects, I think what remains, Blockstack, they're not really doing too much lately. I haven't seen much from them, but they might still be around. They're effectively trying to use the Bitcoin blockchain as a trust anchor and add some additional systems on top of it to do blockchain-based stuff. What we're talking about effectively. There's ENS, which is on Ethereum, and there's Handshake. And there's also Namecoin. It's still chugging along. What's needed for DPKI? For people working on different blockchain namespaces to agree on a standard set of blockchain TLDs. We'll see how that goes. For a web browser like Brave, for example, to support resolving these TLDs securely. Brave actually does resolve, I think, ENS, but it does not do it securely. Brave sends ENS queries by, I don't know if it's by default or if you enable it, but it's a single connection to a single entity. The way that this is done also has to be engineered correctly. You can have fake DPKI where your browser is talking to a single company that is responsible for resolving it. That company is running a full node, like an Ethereum full node, and it is resolving the names and doing the key value mapping for you. But you are trusting that one company to not be compromised. That's not ideal. One way of addressing that is to have your browser talk to two independent companies that are doing that. That will greatly reduce the result of your connection being compromised, because both of those independent entities would have to be compromised at the same time. But there are other ways of doing this, and that is to have something called a thin client on the inside the browser itself, or in your operating system stack, that is talking to the blockchain network and to all the blockchain nodes out there, and is doing something similar to SPV, simple payment verification, which is a very efficient way of verifying that these key value mappings are at the very least accepted by the blockchain. Like they actually exist in the blockchain, they're real. So yeah, so that's the presentation for that.
Well, let's pause. I'm going to pause the recording because what we need, I'd like to take a break every 50 minutes or so.